number of participants still going up, but yeah.
Yeah, okay.
Kind of converged. Yeah, it looks more stable now. Okay, so welcome back from the coffee break, everyone. So the first talk of this session is by Dominic Williamson from Stanford, who will talk about topological measurement-based quantum computation with only 3 fermions. Dominic.
Okay, thanks, Norbert. Yeah, I think I'm going to kick this day into slightly different gear, so hopefully everyone's ready for some MBQC. And I want to talk about doing measurement-based quantum computation topological version with a slightly different model to the Toric code. We'll go from there. Okay, let's see. Yep. So in case I don't get to the end of my talk, I wanted to say the point now. And the point is basically we're thinking about using this 3 fermion Walker-Wang model, which is a certain stabilizer model in 3D. That's different to the usual model used for the cluster state used for topological measurement-based quantum computation. And we're going to take this stabilizer model in 3 dimensions, put in some kind of defects into it, and then by measuring, as you usually do, just on-site measurements, you'll find some history state that represents some kind of topological quantum computation, and it basically achieves the gates that you want to do, which you put into the state to begin with via these defects, encoded on some sort of surface code. And this is heavily inspired by papers of Robert that did this basically, but for Toric code. And I guess another main part of the talk is we're trying to generalize this to some wider class of models. And this is sort of the simplest example that isn't Toric code, if you like. But I'll get to that reinterpreting kind of this previous results too in terms of Walker-Wang models and sort of one-form SPT models and how that is related to the ability to do this topological MBQC. Okay, so that will be the point. But I need to start with some background because basically we're sort of generalizing something that already exists. So I'll try and explain that and then how what we're doing is slightly different. And I need to, as always, start with the Toric code. So I'll start with the 2-dimensional Toric code. This is some stabilizer model, or you can think of it as a Hamiltonian with local terms where the stabilizer generators are local terms in a Hamiltonian. The qubits, there's 1 qubit per edge of a square lattice in 2D. And the interesting thing about this model is it's in a non-trivial topologically ordered phase, which you can see via its excitations. So it has these string operators that create these excitations, which I've drawn in E. So like a basis I'm using a line of X's along lattice edges gives you some excitations I'll call E of the vertex terms. And if we have like a dual line of Z's, we get some excitations of the plaquette terms, which we call M's. And if you have both, they fuse to something we're calling psi, which is a fermion. And I'll say what that means in a minute if you're not familiar with that. So I think one point to say about this is that these are not just excitations of the like eigenstate excitations of the Hamiltonian, but when you think about having these all local excitations modulo by, so excitations that have an energy penalty that's kind of local in space, modulo local operators, you only get 4 different superselection classes of this. You can have like nothing, or you can have an odd number of E or M's or these psi's. And you can think of fusing these kind of these superselection sectors together by taking some patch where you have one superselection sector and another one, and then blobbing them together and modding out by all local operators over the pair of patches, and you get these fusion rules, which are pretty simple. It's just like Z2 times Z2 fusion rules. So each particle squares to identity, and then E times M fuses to the fermion. And because we're in 2D, we can also have some interesting braiding statistics between these things. So you can come up with a process where you kind of create a pair of E's in your ground state, you move some M's around them, and then delete the E's, and overall you're left with a -1 phase. And this is sort of formalized with the S and T. Well, there's another braiding statistic I'm not going to go into in detail, which is formalized by the T matrix, but the process I showed is formalized by this S matrix. So for each pair of particles in the theory, you can define some statistical process. And for each particle on its own in the theory, you can define kind of its topological spin. Okay, so this is the data, the gauge invariant data that describes the Toric code anion theory. We have this Z2 times Z2 fusion rule, and then we have this S matrix, which, let me try see if people can see if I draw on the slides. Can people see that? Okay, looks like it's working.
Yeah, works.
Yes, so we have these -1 processes, and the ordering of the rows I'm using is 1E. Maybe I should have written this. Yes. Okay, and then in the T matrix you can see this topological spin is -1 for the fermion and 1 for the other particles, which is why we call it a fermion. So to actually have some topological code in this state, you need to introduce some extra ingredients, because everything was abelian so far, so there's no place to encode quantum information. And one way of doing this is to make some kind of what people usually call holes or gap boundaries of the model. This is basically a region where you drive a topological phase transition to the trivial phase, and then you'll have some interesting boundary conditions which you can use to encode qubits. There's two ways of doing this in the toric code phase. Basically, to do such a phase transition, you need to identify some self-bosons in your anyon theory, and then you can try and drive a topological phase transition by condensing them, which means in the new phase, basically there will be some local operator that will delete these particles, whereas in the old phase that was impossible. And for the new vacuum to be consistent, after doing this topological phase transition, you need these particles to be sort of self-bosonic, otherwise the ground state's equal to minus itself or something like that. So there's two choices in the toric code. You can either condense the E particle or the M particle, and they give you two different kinds of holes. You can see from the S and T matrix that each of these is a self-boson. And there's one other ingredient. If you want to really get, when you do this phase transition, if you want to really get the vacuum phase, like a trivial phase and not some other phase, you need that the particles you condense braid trivially with everything else you're not condensing. But you can see from the S matrix that this is true. So for example, if we condense the E particle, this column, then for the M and psi, it has a -1 braiding phase with each of those. So in the new phase, they become confined. Okay, so we have these two different kinds of holes. The E hole, where we can push an E particle from the bulk into there, and it'll just sort of be condensed in the hole. But if we try and push an M or psi particle, it'll have some energy penalty when it reaches the hole because it's confined in there. And vice versa for like an M hole with an E particle becoming confined and the M1 condensing. And this gives us some kind of non-local degree of freedom to work with that we can use to make a topological code. So hopefully this is all familiar to people who think about these things. We have one kind of operator that pushes, for an E hole say, it pushes the E charge onto the hole, and then we have a magnetic string operator that will measure the parity of the number of E charges on that hole, basically, and vice versa for the M hole. So we can use this to define some qubits, and I'm going to work in some convention where each pair of these qubits is in vacuum total charge. If that doesn't mean anything to you, don't worry about it, it's a detail. But basically, you can use these properties of the holes to define some logical operators. So you can have this string operator that moves an E charge between a pair of E holes being your X operator, and the magnetic loop operator that measures the parity of the E hole, and it's going to match over the two holes here because of this vacuum total charge constraint. So you can measure that in either of the two holes. And we have vice versa, the Z string operator, the magnetic string operator that moves a magnetic particle between two M holes, and the dual loop of the E string operator that measures the parity of the number of magnetic charges in this hole. So these give you basically a qubit algebra on each pair of holes. And you can do controlled NOT gates with these, basically because if you kind of track the string operators, as you push one of these E holes around an M hole, you'll see that what was originally, just the X operator is now mapped to this pair of operators, the X on the left qubit and on the right qubit. So you can kind of, if you just play around with this, if you haven't seen it before, you just have to kind of track where the strings go when you move this E around this M, as I showed. And similarly, what was the Z operator on the M hole gets wrapped around this E hole you push between the M holes and becomes a ZZ operator. The ZI operator and the IX operator are left invariant. So this is describing a controlled X gate up to Pauli's, I suppose. Okay, so to actually get the whole Clifford group, we need some other ingredients. And the way I'm going to describe it is using this other kind of defect called twists. So twists come from a different property of anyon theories. They come from some symmetry property. So you might have noticed before that basically if you look at like these two rows and columns of the SMT matrix, that they're exactly, well, they're the same up to shuffling the basis. So basically all the gauge invariant data of this Toric code anion theory, E and M look the same. So if you swap them, you would say basically you have the same theory. And it turns out there's some subtleties to promoting this symmetries of SMT to actual symmetries, but it works here. So these are, swapping E and M is a true symmetry of this Toric code theory. So and it turns out that, okay, there's some other subtlety that this is a non-anomalous symmetry, which means we can kind of implement it with an on-site or locality preserving lattice implementation. So if you apply this symmetry that swaps E and M to like the ground state, it's going to leave it invariant. If we have some single E excitation localized somewhere and we apply symmetry to it, it'll flip this E excitation to an M excitation. Okay, but if we only apply the symmetry in some local region, not the whole space, it actually leaves behind some kind of disturbance at its boundary. So it would have an energy penalty along the boundary, basically. And this is the domain wall of that symmetry. You can then cut this domain wall open, and it will keep some signature of the symmetry, which is that when you push a particle across this domain wall, it has to have basically the action of the symmetry. So in this example, when we push like an E or M particle across the domain wall, it's flipped to M and E respectively. And if you push a psi across, it's just left invariant. Okay. So then when you think, you can ask this question about the super selection sectors, but for the defects at the end of the domain wall. And because you have this sort of twisting of the E and M string operators, you can't talk about a braiding process of a single E with this defect at the end of the domain wall of the symmetry. The only statistical process you can talk about is with the psi particle. So it turns out there's only 2 different distinct defects rather than 4, which we label by the eigenvalue under braiding with this psi string. So a pair of these twists behaves pretty similarly to a hole in some respect. It can have this non-locally stored parity of fermions, basically. So we can push a single fermion onto a twist and it will be absorbed. And we can measure the number of fermions with an E or M string operator going around the pair of twists. So this is formalized in some fusion rules on the left here. If you think about fusing 2 of these defects, then you get some superposition of 1 in psi that was stored as a non-local variable before you fuse them together. And you can flip between them by fusing them with an E or an M. Okay, so similarly to the holes, you can use a pair of these pair of twists to encode a qubit. Again, I'm assuming vacuum total charge. And similarly, again, is you have this sort of what I'm calling the X operator, which moves some fermion between the pairs of twists, and some Z operator, which measures basically the parity of the fermions stored on a pair of twists. So having more structure kind of on your single, on half your qubit actually lets you do some more gates here. So you can do an S gate by kind of switching 2 twists. And I won't go through like exactly how that works, but basically if you kind of go and check, this X operator gets kind of wrapped around the other hole, the other loop, and becomes this X times Z operator. The Z operator is left invariant because the switch you're doing is totally within this loop that was the Z operator. So this ends up corresponding to the S gate. And you can also do a Hadamard gate by switching these 2 twists. So because you're kind of dragging the domain wall with you when you switch these twists, but because you have 2 of these domain walls stacked in the middle, they cancel out again. You're left with the same configuration of domain walls after you do this process. And if you track it, it basically just switches the 2 logical operators. Okay, so with these and the controlled NOT gate, we could have a generating set of Cliffords. But it turns out because you have this sort of fermion operator being your X operator, and fermions braid trivially with themselves, to sort of have bosonic statistic when you braid with yourself, a full braid, you won't be able to get this C-NOT gate between these twist encoded qubits. But if you have a sort of mixed encoding where you have some whole qubits and some twists, you can take the twist one around the hole, and you'll get the C-NOT gate. And you can use that to do teleportation, and then I think get C-NOTs between just the twists. Okay. So that's kind of old background. It's a lot of background, but it's how you do a very rough overview of how you would do Clifford topological quantum computation with Toric code using twists and holes. And then you always need sort of magic state injection, which I'm not going to talk too much about because it's sort of orthogonal. I want to think about only things that are really topologically protected in this talk. And now it brings me to trying to modify this a bit to think about some other models. So there's a very close relative of the Toric code called the three-fermion theory. And basically it amounts to just flipping the self-statistic on two of the particles. So the E and the M now become these fermions. And I have three fermions in my theory instead of one. So I've called them fermion psi red, psi green, and psi blue. They still have this Z2 times Z2 fusion rules at the top there. And the S matrix is exactly the same as Toric code. Again, the only difference is like this T matrix. So you might think, what's the point of thinking about this? It's like you've changed some pluses to minuses and probably everything will be exactly the same as Toric code. But it turns out it's actually a very big difference between these two theories in some sense, because the three fermion theory really can't admit holes, basically, at least in a spin system, because there's no bosons in this theory. You can't condense anything, basically. This also means you can't have a commuting projector Hamiltonian because you can't have a gap boundary to vacuum. And if you have a sort of stabilizer commuting projector Hamiltonian, at least if it's translation invariant in 2D, you really know, like rigorously, you have a gap boundary to vacuum there. So we have to think of sort of a different way of doing things.
Okay, Dom, I think there's a question.
There's a question,
Sure.
but I think I can't unmute anyone. I think I'm the host.
I did it.
I quickly want to ask, since the language now that you're using with red, green, and blue is kind of similar, what is the relation, if there's any, to color codes?
Yeah, I think I'm going to get that in a few slides. So
Okay, thank you.
this is realized by some color code, but I'll say it more precisely in a few slides. Cool. Okay, I think I want to move on. But before I tell you about this relation to any lattice model, let me just say how the twists work. So because we've basically made these three particles identical from the point of view of the gauge invariant data, we have like a much bigger group of symmetries in this three fermion model, which is actually corresponding to any arbitrary permutation of the red, green, and blue that you like. So you have an S3 permutation group of symmetries that will leave theory invariant. And so there's sort of three Z2 elements of this that just switch. So I'll label those green, red, and blue. So they're labeled by the element they fix. So like the green symmetry is just going to fix the green and switch the red and blue, and similarly for red and blue. These domain walls behave very similarly to the twist in the Toric code, except you now have three of them that are different. So there's two different kinds of defects for each of these that are labeled by the braiding with the particle they fix. Then there's another one that's sort of different to the one in the Toric code because it's an order 3 cycle, which just sort of shuffles red to green, green to blue, and blue back to red. And then you're also going to have this element inverse. You're going to call this element tau, so like tau and tau inverse. This one's pretty interesting too. There ends up being no non-trivial string operators that braid with the defect at all. So there's only one kind of defect for each of these domain walls, and it has quantum dimension 2. But I don't need these to get Clifford gated. So for this talk, I'm not going to talk about these further. Okay, they are interesting. So here's just some fusion rules from this defect theory. We have like the three fermion theory tacked onto these different colors of the sigma defects for the Z2 elements of the symmetry, and then we have these Z3 elements. And the Z2 elements, like the Toric code twist, have quantum dimension √2, and the Z3 element has quantum dimension, defect has quantum dimension 2. Okay. So now basically, because you have different kinds of these, we're going to get more gates we can do it now, twist encoding. So a single one of these twist encodings you can think of as almost being identical, besides like the fermionic phase of the string operators involved, which doesn't really show up in these gates. You can do the same things you could do with a Toric code twist encoding. So doing the swap will give you S, doing this swap will give you Hadamard. But now because we have different kinds of these twist encodings, we can do controlled knots between them. Because, yeah, maybe I should just slow down for a second. If we come back to this slide, the string operator, the X operator in the left is going to braid non-trivially with this Z string operator on the right, which is kind of what gives you this non-trivial gate there. So in some sense, it's very similar to the normal toric code because you have these different kinds of holes that can hold some non-local charge that can very non-trivially with each other because they're different. In this 3 fermion model, we have different twists, and these can hold some non-local charge which can very non-trivially with each other when they're different. So for that reason, you can get CX gates. So basically with this twist encoding using different colors of the twists, you can do all the Cliffords you want just with braiding. Okay. So, okay, now I come to how would you do this in a lattice model? I want to go pretty quickly because I want to talk about MBQC things too. But like I said before, there's no stabilizer model for this. But there is a subsystem code, which Hector worked out with some collaborators in this paper. And it's on this weird kind of inflated honeycomb lattice. And I've colored the plaquettes just for reference. It's not actually changing which lattice terms are there. To define the lattice model, it's kind of like Kitaev's honeycomb model. You have these 2-body terms, you label all the edges, and on the bottom left there's like some unit cell of the different labelings which you translate over the whole lattice to tell you what's an X, Y, and Z edge. And then you have these 2-body terms. So the spins are all living on these sites of this inflated honeycomb lattice. And then you have these 2-body terms for the edges, which are either XX, YY, or ZZ, depending if you're an X, Y, or Z edge. And because these terms don't commute, you can have different phases and phase transitions in this model. It's sort of more interesting than the stabilizer model. And if you crank up JZ to be very big, you actually get the color code. It's the stabilizer color code you're used to. Okay. And property of this model, why it's related to 3 fermion theory, is because it has some stabilizer group of like string operators. You have a Z2 times Z2 per plaquette, which are generated by this plaquette X and plaquette Z operator on the left. And you can kind of multiply these up to get big string operators that live on some sublattice, basically. So for like the red sublattice, I can have the string operator built by out of these components I've drawn that will create sort of 2 particles on the red plaquettes at the endpoints. And, well, I should say super selection sectors, because, okay, there can be different phases of this, so the exact particles you get can change. But anyway, just from the property of the string operators, they actually have the 3 fermion topological statistics. So you know, basically, even though this model has different phases and phase transitions, say as long as you're in a gapped phase, you have to have the 3 fermion theory appearing basically as a sub-theory of the topological phase you're in. So that's why you could go into the color code phase, because you can think of the color code anyons as being 2 copies of 3 fermion. This actually turns out to be non-chiral, so you can realize it in a stabilizer model. But if you kind of drive this into a really generic phase where you get rid of as much of the super selection sectors by condensing them as you can, the only stuff left is like the 3 fermion sub-theory, which is kind of, as long as you have these, it's sort of protected by the stabilizer group symmetries of this model. Okay, so I'm just trying to rush through this because I want to get to MBQC, but in this lattice model, we can already sort of implement these defects, these symmetries and defects. So because you can think of roughly the fermions, the 3 different kinds of fermions as living on the 3 different sublattices, you can see that the lattice symmetries are going to shuffle these around. So first of all, we have like, for the Z2 generator, we have this like rotation by 2 pi on 6 around the different colored plaquettes. So if I have like this rotation around one of the green plaquettes, like here, it's going to rotate. So if I'm rotating about this plaquette, it's going to rotate these plaquettes as follows. And you see it overall on the topological data, it will just swap the red and blue particles and leave the green ones fixed. When you do this symmetry on the lattice, you actually need to also do a Pauli that swaps X and Y on every site, but that's not super important. And then for the Z3 elements, you see like a simple translation along one of the lattice vectors. We'll implement that. It'll switch red to green and green to blue and blue back to red. So we can use these lattice symmetries to put in lattice defects, which will be like a lattice version of these topological defects, symmetry defects I mentioned earlier, but it's kind of inconvenient. So there's like a well-defined procedure for putting these lattice symmetry defects in. I didn't do a link, but there's a sort of nice paper by Else and Thorngren that talks all about this and classifying lattice SETs. And it's pretty simple to put these into this model, but you have to sort of deform the lattice. So for the disclination defect, you have to really cut out some like 2 pi on 6 wedge of the lattice, and then stitch it back together by putting in these edge terms that you cut, which will be some mixed edge terms that will be like x, y edge terms, because they kind of cross this defect that did the x to y symmetry. You can also have a sort of more traditional dislocation defect, which I've drawn on the right, that will be one of these order 3 defects. So in principle, we could kind of try and use this lattice model to actually do this 3 fermion defect Clifford, topological quantum computation. But for various reasons, because it's like a subsystem code with quite big stabilizers, and also you have to actually sort of screw up the lattice when you're making these defects and moving them around, it's sort of maybe not ideal. And yes, it's not what I advertised at the start of the talk, so maybe this was kind of a bait and switch, but I'm going to address that now. At the start of the talk, I said, yeah, we were going to take this 3 fermion Walker-Wang model, which is like a short-range entangled state in 3D, and I was going to have these defects in the lattice, and then I would do measurement-based quantum computation to implement my topological quantum computation. And I'll try and get as far as I can to explaining this, but the point of this is actually in this model that we're trying to do the measurement-based quantum computation in, the symmetry and the defects will be much simpler than this 2D model. And the whole model will end up being a stabilizer model too. So we'll avoid these sort of nasty features of having to use this subsystem code, and also having to have these symmetries and defects that sort of act on the lattice and not just as some on-site or local unitary thing. So those problems won't be there in this 3D model. Okay, but now I've got to introduce a bit more background, hopefully briefly, because I'm introducing a new ingredient, which is doing this topological quantum computation and a measurement-based implementation. So let me just run through MBQC and maybe to the topic of the conference a bit, its relation to SPT, or symmetry-protected topological phases. So lightning review. In 1D, we have like this cluster state, which is just generated by applying some control Z's onto a bunch of plus states with the geometry of like a 1D line. And the interesting thing is it's entangled in kind of the right way, that if you measure in the x basis, which is, so yeah, I'm using maybe slightly weird notation. I'm using this dot to be like a plus state, this dot with the line coming out of it to be a plus state, and this pair of dots with a box in between them to be a control Z gate. Okay, so then if we measure onto this, in this plus basis, which is represented by a bunch more of these dots, and then the Z to account for whether you get plus or minus outcome, what you're left with is some maximally entangled state on the end spins with a Hadamard implemented on it up to some Pauli correction. And so the first thing is, it turns out you can actually pick sort of different measurement bases to get whatever single qubit gate you like instead of Hadamard. And then the second important thing is that this measurement-based quantum computation implementation of like sort of single qubit gates kind of persists throughout the whole symmetry-protected topological phase. I don't want to go too much into 1D SPT phases, but this is a kind of topological phase you can define in the presence of a symmetry the state has. And as long as you respect the symmetry and you're within this phase, you can kind of, at least to some approximation, keep doing this MBQC. So it's tied to the properties of the SPT phase. To get universal gates with this, you need some 2D state, call it also the cluster state, on the vertices of some square lattice, where you just prepare it again by doing control Z's between nearest neighbors. And now you kind of have to use your measurements to sort of imprint the circuit you want to do onto the state. So you kind of measure in the Z basis to disentangle stuff, and then in the X basis to make these entangling gates. And roughly you're going to get like a controlled Z gate between these different decoupled wires that you've decoupled by doing the Z basis measurements. Along each single wire, it's like the 1D case again, so you can do your single qubit gates as desired. But now, because you have these lines joining the 1D wires, you can do entangling gates between them. And this is enough to get universal quantum computation. So this is really cool, and actually even more cool, it also has some relation to a sort of symmetry-protected topological phase, which has been kind of popular in the last few years. Called a subsystem SPT phase. So it has like a big extensive or sub-extensive group of symmetries that's kind of given by rigid lines. and as long as you're in the phase that sort of obeys this symmetry, to some extent to some approximation, your MBQC, your universal MBQC still persists. Okay, so how do we sort of combine this with topological quantum computation to actually get protection on the encoded qubits that we're simulating quantum computation on? So a naive thing you could think would be like, yeah, each of these single spins you kind of concatenate with some Toric code to give you like a 4D model, but it turns out you don't actually need to do that. So Robert also already worked this out. You can do this in 3D using a different kind of cluster state on the faces and edges of a cubic lattice, where you have these sort of 5-body cluster terms, translation invariant. And you have one of these for each face and each edge of the lattice. And the main point, to give a very brief overview of this, is that you have Toric code anion theory supported on the boundary. So maybe to say more precisely what that means, like you can find some string up, you can find a certain boundary condition that this is sort of gapped, and so stabilize a model. And you have string operators that just have the same statistics as Toric code, and non-trivial superselection sectors at the ends of these things on the boundary, even though the bulk is kind of in a trivial phase. Okay, and you can also sort of make holes in the boundary by picking a different boundary condition, and then you can sort of simulate this hole-based topological quantum computation by measuring. So if you measure in sort of the right basis to introduce some holes and braid them, you'll be implementing the corresponding topological quantum computation that sort of history corresponds to between the initial surface state and the final surface state. So this is just a way of sort of taking what you could do with like deforming things in a 2D Toric code and implementing on the boundary of some 3D SPT model using measurement. Okay, and that's what we kind of want to generalize. Oh yeah, and okay, to connect to SPT phases, this bulk model here has this thing called a one-form symmetry, which is like on dimension 2 submanifolds, you apply some symmetry operator, and the ground state will respect that. And the connection with the SPT phase and the MBQC is that I think as long as you're kind of in this SPT phase, this MBQC should function pretty well. Although I don't know if that's totally proven, but at least in this case, you actually have like some non-trivial non-zero temperature region of this SPT phase, and I think it has been shown that this kind of works if you're at sort of finite temperature but without Hamiltonian perturbations, and you're still in this SPT phase. But let's say sort of vaguely the idea is this should work as long as you're in this SPT phase, and I will talk more about why I think that is in a minute. But so for me to kind of understand this thing, I was trying to link this to something I already knew about and to generalize it. And there's this class of lattice models called Walker-Wang models that have, for the purposes of this talk, you can think of them as basically taking in one of these anion theories like Toric code or 3 fermion as input. They make some commuting projector Hamiltonian as the output on a lattice of qubits on edges of some cubic lattice. And the point of the model is although the bulk is kind of in this trivial phase or short range entangled phase, on the boundary you have the state, the anion theory you put in is realized there. So in particular, you can actually put in one of these chiral theories like 3 fermion, and that will give you a way of getting a commuting projector model on the boundary for these chiral models. So if we put in Toric code, this sounds very similar to the RVH cluster state, right? And it turns out that all you have to do is kind of shift lattice to dual lattice in the cluster state, and you exactly get one of these Walker-Wang models. So here, I mean, you take basically the green spins and shift them onto the blue spin lattice in the way I've shown. And then those Hamiltonian terms I was writing on the new lattice now look like this. And if that's unfamiliar to you, that's okay. Basically, that's exactly the same thing as like Walker-Wang model for Toric code. So they're really exactly the same, up to just shifting the lattice. The nice thing about this Walker-Wang picture, besides that it is part of like a quite general framework, is that you have a nice interpretation of sort of the ground state. So in this case, we can assign each of the spin configurations on the edge to one of the anion types of the input model, in this case toric codes. So I've got some map of how you could label your different spin states by the toric code anion lines. And then you can reinterpret these plaquette terms as basically just fusing in one of these anion lines into the lattice. And the important part why this is sort of different from the usual toric code is that you have these little dangling terms besides the normal plaquette term, and those come from the braiding you put into the theory. So if the braiding was trivial on the theory you input rather than being non-trivial anion theory, you wouldn't have these terms. And okay, one other thing I should mention in this slide, I didn't mention these terms. These are like just some vertex terms. They're actually products of the plaquette terms in this case. So you don't actually need to include them as extra terms, but in the more general Walker-Wang model, you do include these terms separately. And these terms are just enforcing some kind of fusion rules on your string types. So in this case, it's like the Z2 times Z2 algebra. Okay. Yes, so the ground state of this model is basically like one of these kind of string net condensed states, if you like. You have like a sum over all allowed string configurations that satisfy the fusion rules, and then you have some phase or weight associated to them. In this case, it's just like some linking -1 to some linking number between the red and blue loops in your sort of lattice. And in general, for these Walker-Wang models based on anion theories, there might be some weight, but there's also some part like this linking number coming from the braiding of the configuration you have. Okay, so now if we think back to this topological computation we were doing, and I'll just think about doing kind of the identity gate for simplicity. You will measure in the X basis, you'll get some outcomes you can interpret as literally toric code string, like a history of some toric code string process in this case. If there's some like errors, like physical or measurement errors, you might have broken strings, but you can kind of match them up using perfect matching or something like that. And then you'll have some guess at what you think the history was, and that will tell you exactly like what correction operators, string operators to apply on your final surface. So that's kind of the idea how you would do this topological computation and correction. And then, yeah, you can also do a similar thing if you have more non-trivial stuff going on, like having holes and so on. Cool. So I wanted to get to the 3 fermion version of all this. So the nice thing about the Walker-Wang model, like I said before, is that it's like some super general construction. So in some sense, we're thinking about doing maybe the closest thing to toric code that isn't toric code. But it also already has some of the interesting features, like it's implementing a chiral model on the surface using a stabilizer model in the bulk. And the Hamiltonian for this 3 fermion version of the Walker-Wang model, as you could expect, is very similar to the toric code one. It only differs in the braiding, basically, and actually some subtlety of the braiding because the T matrix is slightly different. So you can see that basically the only difference you get is you get some X terms that didn't show up before, basically. So yeah, very close, but actually ends up giving you totally different boundary theory. And again, the vertex terms in this case are like exactly the same. Cool. So, right. In this case, we can pick some labeling of the spins by anion lines again, and interpret the plaquette terms as just fusing these lines into the lattice. But we'll get a different answer than the toric code case because the rules for the braiding are different. Cool. And the ground state looks almost the same. It's the same kind of configuration, just summing over. It's just that the weight is different now. And kind of surprisingly, I just wanted to point this out as an interesting fact. The bottom reference is underlined here. Just having this slightly different sort of phase weighting actually means that this ground state is kind of pretty drastically different from the toric code one. And this is in some sense just a rephrasing of the fact that this short-range entangled bulk has a chiral theory on the surface. This recent paper found that if you accept some reasonable assumptions, you can show you can't have a local unitary that exactly creates this state from the trivial state. You have to have like a locality preserving quantum cellular automata unitary that does this. And this is actually like a non-trivial QCA. Yes. So for the purposes of thinking about preparing the state, it's not too much of a disadvantage. It means you'll just basically need some ancillary qubits like the way we usually prepare surface code. and then you'll have to do like a local unitary on the normal qubits and the auxiliary qubits, and then measure the auxiliary qubits out to prepare the ground state. Okay. But the upshot of plugging in this 3 fermion model into Walker-Wang was that we got some short-range entangled bulk, 3 fermion Walker-Wang model, which was a stabilizer model, as I showed. And on the boundary, we get this 3 fermion anion theory. So we can try, so the first thing we should say is that basically doing the identity gate works almost the same as in Toric code. The only difference is you'll have some slightly different braiding phases, but these almost don't matter. It's just giving you like some plus or minus ones that might be different in some overall phase of the wave function. So you can do kind of the correction and the identity gate the same way. Yes, I wanted to mention about the same one-form symmetry that kind of lies behind the MBQC in both cases, but I think I'm running out of time a little bit, right? Do I have like 5 minutes left now?
Yeah, 5 minutes for sure.
Okay, so I'll just blast through this quickly. In both of these models, we have the same vertex terms, and these generate this kind of Z2 times Z2 one-form symmetry. So on the dual lattice, you can use these to build up some symmetry operator on like a dual cube, or topologically it's just a sphere, but anyway. And this will be a symmetry of the model. And recently we were kind of, well, why I started thinking about this kind of was because we were thinking about classifying these one-form SPTs. And the way I like to think about classifying these is take the symmetry, cut it open and look at its domain wall, and then think about the algebraic theory of the domain wall. So this will give you like the usual cohomology classification of global symmetry SPTs, if you're familiar with that. But in this case, the domain walls you kind of get of these symmetries are actually just some sort of abelian lines, if the symmetry is abelian. And you could have some sort of more general configuration of these things, and actually the sort of algebraic structure that's describing them is just basically an anion theory, if you like, a sort of generalized anion theory, which is a braided fusion category that describes the sort of topological processes of these defects. And so as long as you're kind of in the same SPT phase, you do some perturbations that are small enough that respect these symmetries. Although the sort of string operator that implements the boundary of this symmetry might be slightly different on the lattice, the topological kind of properties of these defects will be the same within an SPT phase. And so that's kind of the vague point of view why this MBQC should pretty much work throughout the whole phase, because these sort of strings are implementing at the surface will have the same topological data. You'll have the exact symmetry in the bulk because you're preserving it. And the correspondence between basically these string operators on the boundary and this exact symmetry in the bulk, that overall this thing is basically a stabilizer, will hold throughout the phase. So you can still kind of use this history state, which tells you kind of the value of this sort of cylinder bulk operator, and measure these string operators on the surface, and overall those things will give you sort of +1. So you can use like the past history to tell you whether you want to flip or not flip your final string operator to do your correction, if you like. Okay. I still haven't told you how to do the non-trivial gates with the 3 fermion Walker-Wang model. So we wanted to do them with this twist encoding. And to put these defects into the lattice, I need to describe how the symmetry acts on the lattice in this 3 fermion Walker-Wang model. So the most sort of the obvious place to start is on this 2-qubit Hilbert space per edge. You have like this obvious S3 symmetry that's just permuting the states corresponding to the 3 colors of fermion strings. And this is just generated by controlled X going each of the 2 ways on the 2 edge qubits. So you can see that this will basically permute around these vertex terms, which are like the generators of your one-form symmetry. So actually what you have is it's kind of S3 global symmetry. So I'm imagining just taking the tensor product of this S3 action on all of the edges. And you see that this actually acts in a non-trivial way on the one-form symmetry. So overall you have this thing that's called like a 2-group symmetry, because it has this like global part and this one-form part. And they're tied together in like a non-trivial way because the global part acts on the one-form part in like the obvious way. And this is sort of related. This is in some sense just a different point of view on the symmetry-enriched topological order of the 3 fermion theory by some permutation action. If that means anything to you. If it doesn't, don't worry. This is just some interpretation of something going on here. Okay, and then if we think about how this symmetry acts on the plaquette terms, naively, basically, you would just think it just permutes these strings. So it would just permute these plaquette operators. Turns out there's like a slight subtlety, because when you resolve the string operators into the lattice, there's some gauge variant data coming into the model, and only the symmetry is only an exact sort of on-the-nose symmetry of the gauge invariant data. But you can fix that by just applying some gauge transformation. And that ends up being like another part of the symmetry action, which is just a local unitary. So it's okay. So the upshot is basically you have this sort of simple action, which is just the product over all the edges of permuting these qubit states. And then you also have some local unitary part, which is just doing a gauge transformation. But yeah, with that said, that's like technicality, which just means you can, the point is you can just think of this as permuting the kind of string types as you would imagine it would be. So now we can actually think of how putting domain walls and defects of these symmetries into the lattice. So if we think of like the green symmetry domain wall, basically it's just going to flip the plaquette terms that cross it that are not green. So you'll have a plaquette term that's kind of half of the red one stuck to the other half of the blue one. Oh, and just technically to put these defects into the lattice, they kind of live on the dual lattice, but because we don't want to be doubling any spins or anything, we just resolve the spins to one side. So this domain wall will cut through the dual lattice and cut through some qubit edges, and then we just have some rule to resolve them to one side of the defect, so it doesn't cut through any qubits. And it's well defined to say that all qubits are on one side or the other of the domain wall. Okay, so the Hamiltonian along the domain wall is just these kind of stuck together terms from either side. And then if you have a defect of this domain wall, similarly to like the 2D defect in the topological phase, you only have Hamiltonian terms that are sort of fixed under the symmetry action allowed. Because when you go through this defect, you kind of get permuted, and then you have to kind of form a closed loop to give some term that can enter the Hamiltonian. So in this case, for the green defect, you're only going to have these green Hamiltonian plaquette terms on those plaquettes where it passes through, and you won't have the red or blue ones, which gives you some sort of degeneracy associated to the defect. Okay, so with that described, in principle, I've told you how you can put these defects and domain walls into the lattice, and then we have different types of them, like the green and blue ones. And so we can set up some configuration where like they braid, and then we can do our MBQC to kind of push the surface state with the defects through this computation and up to some sort of abelian correction operator, which we can find by looking at the history we're measuring of the state. We can use this to sort of implement our 3 fermion topological quantum computation as advertised. Okay, and that's kind of the whole point. So yeah, there's like a summary. The idea for this is slightly different to the usual cluster state approach. At the moment, at least, we're thinking of putting these defects that do the gates we desire, the Clifford gates we desire, in at the start, and then you just kind of measure through to implement the gate you want on the encoded state on the surface. And then you can kind of use this measurement history to do the correction. And because this MBQC was based on basically the symmetry properties and the defect topological properties, it seems like it should persist throughout the one form SPT phase, but it would be nice to show that rigorously, which we haven't done yet. Cool. I think I should probably end there. Yes.
Well, thanks a lot for this very nice talk. Are there questions? Okay, so there are some raised hands.
Hello.
David.
Hey, Dom. I have a question. So the defects you put in at the start, you don't put it in through measurements of the Walker-Wang state?
Currently, we're not thinking of doing that. I think we could, but yeah.
And I don't know, in the normal model of Robert, do you put them in with measurements, or do you also have to put them in beforehand?
I thought you implemented them with measurements in like a different basis, but I could be wrong.
Correct. No, that is correct.
Okay,
yeah,
thanks.
I think so far for us, maybe I can say the reason why we're doing it this way is because you could obviously like take the original model and kind of measure into the new stabilizers, but they're kind of for these defects, but they're kind of more complicated. It's not like just, we didn't find a way of doing it by just say measuring on a different basis would implement these defects we want. We kind of have to measure the more complicated stabilizers. So
Okay,
it's not quite as nice, yeah.
No questions?
Does time reversal enter anything in the picture here, or like usually we think of that Walker-Wang as protecting SPT with time reversal?
Yeah, that's a good point. I didn't mention time reversal, but in this paper I linked for the 3-fermion model, they actually explain how you can think of 3-fermion Walker-Wang as like a global time reversal invariant SPT. We haven't used that symmetry, but yeah, because I think basically, well, the reason that we didn't think of using that one is because putting in defects to this is kind of subtle. But it is there too, yeah. So maybe it would be good to also think about it and its defects.
Do you think it would protect the phase for computation, or would it be a different thing?
I think we don't need to, well, this is one thing. To do the gates, you might need to also protect the symmetry, but we haven't, because we haven't used that symmetry. We're thinking of protecting the one-form symmetry mainly, which will protect you being in this phase too. So I think you don't need to protect it to still be able to do the computation.
More questions?
So here's Robert has a question. So when you think of stability throughout the phase, are you thinking of varying the Hamiltonian, or are you also thinking about non-zero temperature?
It would be nice to have both, I guess, because I think these one-form SPT phases are supposed to have a non-zero temperature phase. And then if you have the one-form symmetry, they should have like a Hamiltonian perturbation phase. So ideally it would be both, but like I'm not going to claim any kind of proof of anything. It's just.
More questions? Well, if not, let's all thank Dominic again.
Yeah, thank you.